Swayam Prabha. Digital India. Educated India.
Dear all, we so far discussed Unit 1 and Unit 2 and followed with the most important topic is algebra or higher algebra or modern algebra. So, mixing together, and we are going to discuss the modern algebra, rather call it as abstract algebra. So, first let us start with introduction to algebraic ideas. This introduction to algebraic consists of groups, subgroups and their application to cryptograph, and followed with the second 28 module is cyclic groups and their application to cryptography. And then we have to understand the basic ideas about the rings, special rings, fields and corresponding examples. And then fields and finite fields and their application also most important to discuss. Simultaneously we discuss some problem on the above topics, followed with coding theory. That is we have to understand what is encoding and even parity check minimum distance, property of distance function, parity check matrix, then decoding and error correction, error detection and correction group codes, and followed with application of coding theory. So, these are all the topics we are going to discuss this lesson. Now, let us start with the groups. So, it is most important that before starting groups we need a binary operation. See, actually first of all we have to understand the number system. Once again I tell you, n stands for natural number. I start with 1, 2, 3 and so on n, or any finite number, let it be small n, and then whole number I start with 0, 1, 2, 3 and so on n, and maybe finite or infinite, and then we have an integer, start with the minus infinity and so on, minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on infinity, and followed with rational. It is in the form of p by q, where q not equal to 0, where p and q are co-prime integer. It means the GCD of p comma q equal to 1, and then we have rational number, that is terminating, non-terminating, occurring number and countable, and then followed with a real number, say root 2, root 3, e and so on etc. of terminating and non-terminating. So, this is called as number system. So, first understand the number system, then let us start with the binary operation. So, binary, by mean 2, nary mean the operate between the two numbers, say let it be a and b are the two numbers belongs to natural. Then we start a star b, in the sense that you star may be the binary, it may be a plus or minus or multiplication or division or some other operator, dot, circle, like that. You can introduce as your wishes of any operation. So, that operation is based on your definition. Say if you have 2 plus 3, then add them, it becomes 5. If you subtract 2 minus 3, it becomes minus 5, and then if you multiply 2 and 3, it becomes 6. If you divide 2 and 3 is a division. So, like that we have a operation like this. Then we have a circle b, right, equal to a plus b minus ab is as your assumption to define the operation. So, this is called as binary operation. So, try to understand this binary operation on G is a function that each ordered pair of element of G is element of G. So, function mean a map f such that x to y and x and y are non-void set, mean non-empty set. Non-empty mean at least one element in that set. So, if every element in domain must have a unique image in codomain, that is f of x, and if you take x1, then it becomes f of x1, right. Like that we have to define every element in domain must have a unique image in codomain, then it is to be function. Now, define a function that assign each ordered pair, say x comma y is ordered pair, and then we have the notation x star of y, then the star is a binary operation, and then you take an element x comma y belongs to the set G, and G is a non-void set. Keep it in mind this definition. Let us go with the definition of group. So, let G be a set together with a binary operation usually called the multiplication that assigned to each ordered pair A comma B of elements of G, and element of G is denoted by A star of B or AB. We say that G is a group under this operation if the following three properties are satisfied. So, first property is default, that is closure property, that is star is closed. Star is closed in the sense that A belongs to G and B belongs to G, then A star of B, the resultant should be belongs to the same set G, then it is said to be what closure mean. You take an element 2 in natural number and 3 in natural number, then 2 star of 3 mean multiplication, you have a 6, check it out whether it belongs to same set or not, then it is said to be what a closure property. So, keep it in mind this ideas. So, let us go with next definition is called it as associativity, mean this operation is associative, that is you take a 3 element instead of 2 element you take 3 element A, B, C, and then you have to write like this pair A, B and product them and multiply with the C, and this is equivalent to A into BC. So, AB into C equal to A into BC for all A comma B comma C belongs to G. If it satisfies like that, then it is said to be associativity. So, keep it in mind, associative properties satisfy or not, check it out, and then next existence of identity. So, there is an element E called the identity in G such that A star of E equal to E star of A, which is equal to A for all A in G. So, it means you search the identity element in the sense that if you multiply this element into any element in that set, the same element should come, and you have to write left and right of AE and EA, so that it works parka of for all A in G. And similarly, you have to find the inverse of A such that A inverse in G such that A star of B equal to B star of A equal to E. So, and B is the inverse of A, therefore, AB equal to BA equal to E. So, this way we can write what the inverse element of the set G. So, keep it in mind this if it satisfy the all 4 properties, then it is said to be group. Next let us go with one example. You take a set of all integer. It denoted because the German word for numbers is Zaglon. The set of rational numbers Q for quotient, and the set of real numbers R are all groups under ordinary addition. Note that point, ordinary addition. In each case the identity is 0 and inverse of A is minus A. So, let us check z equal to minus infinity and so on, minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on infinity. Now, you take a equal to minus 2 and b equal to 1, you take it under a under star is here plus operation, and then a plus b equal to minus 2 plus 1 equal to minus 1, you check it out, minus 2 belongs to z, therefore, it is closed. So, like that you have to check it out each elements in that set and whether it satisfies the 4 properties or not. So, second one is a plus of b plus c equal to a plus b plus c, and for all a comma b comma c belongs to z. Say let a equal to minus 2 and b equal to 1 and c equal to 2, you take it and substitute here. So, that minus 2 plus of 1 plus 2, which is equal to minus 2 plus 1 plus 2 and minus 2 plus 3 here, and here minus 1 plus 2 here. So, the resultant is a plus 1 and plus 1, therefore, it satisfies associative property. So, it is called it as associative property. So, that way we can do for what, whether it is a closed or associative. Next we have to check it out. The third property is existence of identity. So, a plus of e equal to e plus a equal to a. So, you take one. So, which element we have to take it, so that element should be the same. So, you have to search that 0 is the only possibilities of what 0 is the only possibilities of that element added. So, that the resultant will be 1, implies existence of identity satisfies. So, here e equal to 0, and therefore, the 0 you check it out whether it belongs to z. Yes, definitely it belongs. And fourth one, a star of a inverse equal to a inverse star of a equal to e. It means a plus of minus a equal to minus a plus a, it should be 0 comes. So, if you take one a as a 1 or a as minus 2, suppose a equal to minus 2, right, then it becomes minus 2 and plus of minus 2, so that it becomes minus 2 plus 2, so that the resultant will be 0. Similarly, you have a minus of minus 2 plus minus 2, and then we have a 2 minus 2, which is equal to 0. Therefore, it satisfies what existence of inverse. If it satisfies all the properties of definition of a group or law of the group, then the G is, then the set Z comma plus is a group. So, this way initially you have to check it out whether the set of all integer is a group. Similarly, we take instead of Z as Q, right, the Q, then it is the form of P by Q, where Q not equal to 0, where P and Q belongs to group prime integers. So, obviously, here E equal to 0 and inverse E is the inverse of A will come, say whatever may be the element, beautifully we can write the inverse of E. And note that similarly for the real we have 0, for real we have E equal to 0 and corresponding inverses of each element occurred, and it satisfies the whole 4 properties, then we say that it is a group. Next, some more example we are going to see that the set of integer under ordinary multiplication is not a group. Set of integer under ordinary multiplication is not a group, because one is the identity, the property 3 fails. For example, there is no integer b such that 5b equal to 1. So, that is why set of all integer in ordinary multiplication is not a group, because 0 is also included, z equal to minus infinity, minus 3 and so on, minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on infinity. Now, 0 is also included and 0 does not have an inverse, therefore, property number 3 fails, therefore, it has no inverse, therefore, 5 into b equal to 1, like that does not works. This way we have to identify whether it is a group or not. So, here set of all integer is not a group. Next example, the set 1 minus 1 I minus I of the complex number is a group under multiplication. Note that the subset minus 1 and its own inverse, whereas the inverse of I and is minus I and vice versa. So, let us do with the Cayley table, so that you can understand the Cayley table of whether it is a group or not. So, we have to take star is a multiplication, you take 1 minus 1 I minus a, the subset, the sense that it is a quadradian 8 group and this is a quadradian 4 group, therefore, quadradian 4 group is a subset of quadradian 8 group. So, 8 group means we have to additionally add j comma minus j, k comma minus k, so that quadradian 8 group will come. Here it is quadradian 4 group, therefore, we can say it is also a subset of that quadradian 8 group. And then here 1 minus 1 I minus I, it is called it as a Cayley table. In the Cayley table, the matrices you consider this is a 4 cross 4 of the matrix. Inside the elements you check it out, all are what we have chosen the set quadradian 4 group, that is Q4, the same elements are repeated. Then it means through the table we can easily understand whether it is a group or not. Mentally we can check whether it satisfies the closure property or associative property, and then existence of identity, then existence of inverse. Let us start with the closure property. You multiply any one of the elements to from the column to the row, and then you can see the elements will be reflected in first row, second row, third row and fourth row. Seems that all the elements in the same set, what we have chosen the set, therefore, it is closed. And then you take 3 elements, and any 3 elements you take it and multiply them, that also satisfies, that is A star of B star of C equal to A star of B star C, that is you take 1, A is 1 star of minus 1 into I, you take it and then it becomes minus 1 into I. Here you have to take in a bracket in different way, right. So, that is 1 star of minus 1 into I, you take it. So, it become 1 star of minus I. So, here minus I, here minus I, therefore, it satisfies, implies associative property. This is associative property, satisfies. So, it is obviously that it is closed, and then followed with it satisfies the associative property. Next one is existence of identity. You see in the row as well as column, if you multiply that element, the resultant is 1 comes, then that is identity. Here first row first column is 1, and second row second column you see the 1 come, and whereas third row third row and fourth column we have a 1, and fourth row and third column we have a 1. So, these are all the identity come for each rows and columns comes 1. See, check it out, for the column wise also 1 will reflected. Therefore, existence of identity comes, and then we will move to the existence of inverse. So, where we got that 1 in the entry cell, the corresponding rows and columns is the inverse of the other. Here the 1 is inverse of 1, and minus 1 is the inverse of minus 1, and I is inverse of minus I is the inverse of I. So, it satisfies the inverses. That is why the inverses of I and minus I and vice versa of its own inverse will reflected through Cayley table. Therefore, you can understand with the help of the Cayley table whether the set is a group or not. Now, we move to the example 4. The set of all rational number, you take a positive rational numbers is a group under ordinary multiplication, because everything having the inverse a and 1 by a, and then a inverse exist, implies the set of all rational number is a group. Another example, the set S is a positive irrational number together with the 1 under multiplication satisfy the 3 properties of the group of the definition, but it is not a group because root 2 into root 2 is 2. So, S is not closed under multiplication. So, this is the examples of group, not group, and so on. Next, we have to take a rectangular array of the form of the matrix 2 cross 2. A, B, C, D is called a 2 cross 2 matrix. The set of all 2 cross 2 matrices with the real entry is a group under component wise addition. Therefore, A1, B1, C1, D1 plus A2, B2 plus C2, D2 mean corresponding entry you have to add this corresponding entry add, so that the resultant is said to be what? A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, and because of addition property matrices we are using, therefore, existence of identity is 0 0 0, and the inverse of each is only the negative of that element. Then only we can do for what say the properties of A star B belongs to the set matrices 2 cross 2, and A star of B star C equal to A star of B star C works. Here star is matrix multiplication, sorry, matrix addition. Here star is matrix addition. Therefore, you have to do with the help of this axioms. Therefore, A star of E equal to E star of A equal to A, and then A star of A inverse equal to A inverse star of A equal to E. So, if it satisfies these 4 properties, then it is said to be a group. I hope all of you can understand simple matrix multiplication. So, for the inverse you have to take A, B, C, D, and for identity we have which element we can add, so that the same element will come. Only thing is we have 0 0 0 and then A plus 0, B plus 0, C plus 0, D plus 0, we have A, B, C, D. So, existence of identity will come, and then we have a matrix A, B, C, D, and then minus A, minus B, minus C, minus D, take it, so that it becomes 0 0 0 0, because A minus A is 0, B minus B is 0, C minus C is 0, D minus D is 0, therefore, it becomes what? 0, 0 is a identity implies. So, this is A inverse, so this is A inverse and this is A, so A plus, like that. So, we can denote the small a here, small a is represent corresponding matrices here. So, or replace this small a is capital A, so that A star of B belongs to M 2 cross 2, A star of B star of C equal to A star of B star C, and then A star of E equal to E star of A equal to A, and then A star of A inverse equal to A inverse star A, which is equal to E. Here star is denoted plus operation. So, keep it in mind this, so that the example 6 is a group of 2 cross 2 matrices. Now, we are going to discuss one more example, the set integer modulo n, right, 0, 1, 2, 3 and so on, n minus 1 for n greater or equal to 1 is a group under addition modulo n for any j greater than 0 in integer modulo n. The inverse of j is n minus j. This group is usually referred to as a group of integer modulo n. So, you take n equal to 2 here, therefore, it is integer modulo 2, mean the set consists of 0 comma 1, right. So, it means the Cayley table you can do that for integer modulo 2, right. So, we have a 0 and 1, 0 1 here. So, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is a 2, under modulo 2 it becomes 0. So, call it as modulo technique of integer modulo technique. So, that if we have a Cayley table, so here it satisfies group property because it is closed, and then it is associative as well as existence of identity is 0 and 1 having the inverse 1 and right 1, that is 0, wherever 0 comes is inverse of the other. So, 0 having the inverse 0 and 1 having the inverse 1, therefore, it satisfies the inverse property, therefore, it forms a group. So, we can extend this problem 7 to n equal to 3, n equal to 4 and so on, n equal to n. So, that the set of elements consists of 0 to n minus 1 element, and check it out whether it is a group or not. Next example, you take a set of all real number is a group. So, we can infer that G comma star is a group, then it satisfies star is closed, number 2 star is associative, number 3 star is existence of identity, and star is satisfy existence of inverse. So, we can infer that a set satisfying first two property is called it as semi group, and the first 3 properties satisfied monoid, and first property first and fourth satisfies, then it is said to be a subgroup, and if all the properties satisfies, then it is said to be group. And one more property is called it as abelian group or commutative property satisfy, then it is said to be abelian. So, group with abelian is said to be abelian group, and abelian means A star of B equal to B star of A for all A comma B in G. So, G is a non-void set. If it satisfies like that, then it is said to be what? Abelian group. Now, keep it in mind these properties and definition, so that you can understand the depth of the properties of the groups and how the elements we have to choose, and what are all the properties required, whether the group having the inverse or not, and these are all the things we can understand the group structures.